So before we go any further to talking about quantum numbers, we need to talk about a concept known as nodes. Now, nodes are a very specific mathematical term. When we are looking at the wave function electron, we are looking at the density, the probability density of finding the electron. So whether we have a 10%, 20%, or 90% chance of finding the electron. Nodes represent a 0% chance of finding the electron. So what they do is they basically represent gaps in the electron density. Now they have special properties in that, first of all, they are two-dimensional structures. So they look like sheets of paper. The second is that they're going to basically break up our electron density and raise the energy. Because electrons approach these nodes, they can't actually get to them. If they get to the nodes, there's a 0% chance of finding them. So what they do is they basically bounce off. Now there are two types of nodes. The first is the planar node. Now the planar node for something like a p orbital is kind of easy to see. Basically it looks like a sheet of paper perpendicular to the principal axes x, y, and z. But they can take on complicated structures. They can look for the p, for the d and the f orbitals. These end up being really complicated structures. But the thing with planar nodes is, first of all, they extend infinitely out into space. So they're not self-contained, they have infinite area. The second thing is that they're going to break up the electron density along the Cartesian axes, the x, y, and z. So as we look at planar nodes, basically we're seeing that if we were to orbit around the nucleus, we would hit planar nodes, because basically they're preventing the electrons from going from the negative x to positive x, negative y, positive y, negative z to positive z. Basically they're there to keep you from going around the axis. The second one are the radial nodes. Now the radial nodes are different from the planar nodes in that, one, even though they're two-dimensional sheets, they have finite area. So they're not going to extend out to space. They're actually limited to how big they are around the atom. The second thing though is that they're not going to really affect our ability to go around the Cartesian axis, so x, y, and z. If we're at a constant radius around the atom, typically we don't see the radial nodes. The radial nodes limit our ability to go away from the nucleus. So if we were extending as a function of radius, we would definitely see the effects of the radial nodes. So the radial nodes basically, instead of breaking up the electron density in terms of x, y, and z, it breaks it up in terms of shells away from the nucleus. And this is a concept we're going to carry with us as we start talking about the principal quantum number n, as well as the angular momentum.